Rather than forming a sharp image, a single lens typically forms an image that is slightly out of focus. This lack of sharpness arises because the rays originating from a single point on the object are not focused to a single point on the image. As a result, each point on the image becomes a small blur. The lack of point-to-point correspondence between object and image is called an aberration. One common type of aberration is spherical aberration, and it occurs with converging and diverging lenses made with spherical surfaces. Here we show how spherical aberration arises with a converging lens. Ideally, all rays traveling parallel to the principal axis are refracted so they cross the axis at the same point after passing through the lens. However, rays far from the principal axis are refracted more by the lens than are those closer in. Consequently, the outer rays cross the axis closer to the lens than do the inner rays, so a lens with spherical aberration does not have a unique focal point. Instead, as the drawing suggests, there is a location along the principal axis where the light converges to the smallest cross-sectional area. This area is circular and is known as the circle of least confusion. The circle of least confusion is where the most satisfactory image can be formed by the lens. Spherical aberration can be reduced substantially by using a variable aperture diaphragm to allow only those rays close to the principal axis to pass through the lens. Here we see that a reasonably sharp focal point can be achieved by this method, although less light now passes through the lens. Therefore, the image is in better focus, but dimmer. Lenses with parabolic surfaces are also used to reduce this type of aberration, but they are difficult and expensive to make. Chromatic aberration also causes blurred images. It arises because the index of refraction of the material from which the lens is made varies with wavelength. For instance, when sunlight is incident on a converging lens, the light spreads into its color spectrum because of dispersion, similar to that observed when sunlight passes through a prism. For clarity, however, we show only the colors at the opposite ends of the visible spectrum, red and violet. Violet is refracted more than red, so the violet ray crosses the principal axis closer to the lens than does the red ray. Thus, the focal length of the lens is shorter for violet than for red, with intermediate values of the focal length corresponding to the colors in between. As a result of chromatic aberration, an undesirable color fringe surrounds the image. Chromatic aberration can be greatly reduced by using a compound lens, such as the combination of a converging lens and a diverging lens. Each lens is made from a different type of glass. With this lens combination, the red and violet rays almost come to a common focus, and thus chromatic aberration is reduced. A lens combination designed to reduce chromatic aberration is called an achromatic lens. All high-quality cameras use achromatic lenses.